Okay, we're going to wrap up speculation. We're going to talk about speculation to improve parallel programs. In the past few modules, we've actually talked about using speculation in parallel machines to improve the performance of sequential programs. And the idea was in general called thread level speculation, where you would take a single instruction stream and divide it speculatively into threads such that you can parallelize that instruction stream such that you can get higher performance out of it. Here, our focus will be on already existing parallel programs. How can we use speculation? The idea of doing something before you need it, or before you know you need it, to improve the performance of these parallelized multi-threaded applications. And here are a bunch of readings. We're going to cover some seminal readings, some interesting readings, and this is for your reference. This will be posted on the website, module website. And these readings start from Hurley and Moss's seminal paper on transactional memory and speculative lock elision and speculative synchronization papers, accelerating critical section execution with asymmetric multi-core architectures, which you've read. The original paper by Jensen et al. That introduced load linked store conditional operations, that was a precursor to transactional memory. And a bunch of papers, the last four papers are on recent implementations of transactional memory in existing processors by IBM, Sun, Intel, and AMD. We'll cover some of these readings as we go along. But what is the goal of speculation to improve parallel programs? Basic goal is to reduce the impact of serializing bottlenecks, in particular locks or critical sections. The goal is to improve performance and improve programming ease. And in this case, programming ease will be one of our utmost concerns. And that was a concern for sequential, using speculation to improve the performance of sequential execution as well, right? In that case, we didn't want the programmer to create the threads to begin with, but we wanted to use the underlying parallel hardware, multi-threaded or multi-core or multiprocessor, and have that hardware to automatically extract parallel threads out of a single thread of execution. Here, the goal was to improve performance as well as improve programming ease. The programmer didn't need to write parallel programs to exploit the underlying parallel hardware. Here our goal is very similar, except the parallel program is already written, but there are potentially some bottlenecks in it that can cause serialization. And it's difficult for the programmer to improve the performance of the parallel program to optimize these serializing bottlenecks, for example, locks, critical sections, barriers, bottleneck pipeline stages, which we had discussed in an earlier lecture on asymmetry. The key idea is why don't we design hardware to do speculative execution to improve the performance of such bottlenecks as well as improve programmer ease, because the programmer doesn't need to worry about these bottlenecks. One early example of this is transactional memory, which we will cover. In this case, basically the programmer specifies what should be executed atomically, and the runtime system and the hardware figures out how to do that. Basically, the programmer doesn't use locks, which are hard to program with, as we will discuss. The other example is speculative lock elision, which is basically transactional memory that is not exposed to the programmer, at least not exposed as much to the programmer. The programmer programs in locks, but the underlying system elides those locks when the locks are not really necessary. Basically executes critical sections in parallel if it's deemed that these critical sections actually do not conflict with each other. Martinez and Torellis' paper on speculative synchronization is very similar to speculative lock elision paper, except it is also applicable to barriers. And these two papers are worthwhile reading. And this is Roger and Goodman's final paper on transactional lock-free execution of lock-based programs. Again, the programmer programs using locks, and the underlying hardware ensures that those locks are executed concurrently. The critical sections that are protected by the same lock are executed concurrently if they can be executed concurrently in a serializable, in a fashion without data conflicts. Right. So let's take a look at first speculative lock elision, and then we'll jump into transactional memory. These are the two approaches we will cover. And these approaches bear a lot of similarities with each other, and the key distinction is speculative lock elision is not exposed to the programmer, whereas transactional memory is exposed to the programmer, so it does change the programming model. And we will see, I will ask you to compare and contrast these on your own, and think about what are the advantages and what are the disadvantages of speculative lock elision versus transactional memory. So speculative lock elision, many programs use locks for synchronization. This is one of the synchronization constructs that we've covered earlier. Actually, there are other synchronization constructs like barriers and also pipeline parallel stages. And these synchronization constructs can also benefit from similar ideas, and I'll let you think about how to apply these similar ideas that I'll discuss to those synchronization constructs. And many locks, the observation is that many locks are actually not necessary. They're there for correctness, preserving correctness, but these locks are not necessary. Do not need to serialize execution. For example, there are two main reasons for this. One is you may need a critical section to protect some updates to shared data, but those updates may occur very infrequently. For example, you need a critical section to check, for example, let's say you insert an element into a list after checking some condition, and you need a critical section to protect that access, update of the shared data structure, but that update may not occur all the time because it's protected by a condition, and that condition may be infrequently true. For example, a store to a hash table may occur only infrequently during its execution, right? And it may only update the data in the hash table once in a blue moon, right? But you still need to protect that hash table because there may be a reader that reads at the same time that hash table is being updated, that store is happening, and every time you execute an access to the hash table, that reader needs to go through a lock and request exclusive access to the hash table, even though that store occurs only once in a blue moon. For correctness reasons, every critical section, every access to that hash table needs to be protected through that lock, even though most of the dynamic accesses are actually unnecessary. This is called dynamically unnecessary synchronization. Statically, the synchronization is necessary because at some point in time, there may be a case where a store, an update to a data structure can coincide with the reading of that data structure, but dynamically, many times over the execution of the data structure, you may not get any updates. Okay? That's one of the reasons why locks are unnecessary, because the store to the shared data structure doesn't occur frequently during execution, but reads may be much more common. And the second reason is programmers, actually the first reason occurs because programmers can be conservative also, right? They can actually protect the data structure overtly. The second reason again occurs because the programmers are conservative, because updates can occur to disjoint parts of the data structure. This is more about the programmer actually. For example, think of a hash table and think of having multiple buckets in the hash table. Accesses to one bucket in the hash table can actually proceed in parallel with accesses, actually updates to another bucket, right? Because these two buckets in the hash table have nothing at all to do with each other. If I had to visualize what I have in mind, if you think of the hash table, basically hash table, you get an access, you get let's say an address, and you hash it in software and gets into a bucket, and let's say address 1 goes to this bucket, and let's say you're searching for address 1 in the linked lists that's associated with that bucket. This is one implementation of the hash table. This search of that address 1 in the hash table has nothing to do with, let's say, you're actually inserting address 2 into the hash table, but it happens to map to this bucket over here, and this insert operation into the hash table will update this linked list and not this linked list. So they have nothing to do with each other. But the programmer may protect the entire hash table with a single lock for programming ease, right? And that protection of the entire hash table serializes these otherwise potentially parallel requests, right, that go to different buckets, which means that you first need to use address 1 and search for it, and then only after that you can update address 2, which maps to a different bucket. So these have to be serialized because there's a single lock that protects the entire data structure. Now this happens because whereas because the programmer was actually conservative, right? The programmer can actually protect have a lock for each bucket, right? Basically, the programmer can have lock 1 for bucket 1 and lock 2 for bucket 500, right? Or lock 500 for bucket 500, basically. The programmer can have as many locks as the number of buckets, or maybe some other granularity. And this way, now the programmer needs to manage all of these different locks in a fine grain, but now accesses to this bucket and to this bucket don't go through the same lock. As a result, you can eliminate this need for serialization because of mutual because you have the same lock, a single lock. Now you've eliminated that single lock. You've distributed the lock across the buckets. So this is actually easy to eliminate, but many programmers program conservatively. It's harder to program with finer grain locking, right? Finer grain locking is more difficult to implement because of the finer grain, exactly. You need to manage more locks. Whereas coarse grain locking is easier to implement for the programmer, but that leads to dynamically unnecessary synchronization. That leads to updates occurring to disjoint parts of the data structure, even though those updates having nothing to do with each other, and that leads to serialization. So these are the two reasons: stores occurring infrequently during execution and updates occurring to disjoint parts of the data structure are the two reasons why many locks are unnecessary. So the key idea, once you observe that many locks are actually unnecessary, speculative lock elision speculatively assumes that the lock is not necessary and executes the critical section without acquiring the lock. That's the key idea. And while during the execution of the critical section, the runtime system, or the hardware in this case, checks for conflicts within the critical section. If two instances of the critical section are executing concurrently, the speculative lock elision mechanism checks for conflicts, and if they do actually conflict with each other, rolls back the execution if the assumption was incorrect. The assumption is that the lock is not necessary, and those two executions of the same critical section can proceed in parallel because they're updating different parts of the data structure, or they're not conflicting with each other because there's no data conflict. And the system checks if that assumption is actually true, and if that assumption is not true, then the system rolls back execution and restarts. That's the idea. So these are actually from the paper, and the idea is described in the Rajwar and Goodman paper on speculative lock elision, enabling highly concurrent multi-thread execution. This is one of your required readings. And this shows dynamically unnecessary synchronization here, the two cases. Here, one example is you have lock and unlock, and the update is actually protected by an if condition, and that if the condition is not usually satisfied, which that means that this critical section is usually not necessary. Right? Here is the example where I described on the board over here with the hash table. Basically, you have a single lock for the entire hash table, and you do lookups for x and y. And if these x and y happen to map to different buckets, then there's no need for these two to be protected by the critical section when they're executing concurrently. Okay? So what are the issues? Basically, speculative lock elision, what it does is, with the semantics of a critical section, speculative lock elision tries to elide the lock, right? It assumes that the critical section is not necessary. But the semantics of the critical section still need to be satisfied because it's there for correctness, right? And the semantics of a critical section is either the entire critical section is committed or none of it. So how does speculative lock elision actually provide that? Basically, there are many issues to solve in speculative lock elision, especially if you would like to do this transparently to the programmer. First, and the SLE paper talks about how to do this via hardware, purely in hardware. There are several issues. First, the hardware somehow needs to detect the lock, right? If there are lock instructions, this is relatively easy. But many ISAs actually lack the lock instructions. They have constructs that actually implement synchronization using different instructions, like compare and exchange, for example, in x86. And these instructions need to be detected to detect the lock, right? As well as detect the unlock, corresponding unlock. So you need to delineate the critical section boundaries. Remember, in bottleneck identification and scheduling, we had the bottleneck call and bottleneck return. This was published in ASPOS 2012, and this was in our asymmetry video. Basically, those were there to delineate the critical sections or the bottlenecks. Here, if you're doing it purely in hardware, you need to somehow detect the lock. And the paper discusses that. I'd encourage you to look at that. The second issue is how to actually keep track of dependencies and conflicts in a critical section, right? Basically, how do you actually ensure that you know what the critical section read or wrote to? This is very similar to thread level speculation as we discussed earlier, right? How to actually parallelize single-threaded applications. Basically, you need to somehow keep track of what is read by a critical section and what is written by a critical section. And remember, in thread level speculation, what we did was we added extra bits to different memory locations, either the cache or address resolution buffer or a special store buffer like the address resolution buffer, saying this location was written or read by this critical section. Basically, each cache line had a read bit and a write bit added to the tag store, tag entry. We can do a similar thing, right? Basically, we can keep track of the read set and the write set of the two critical sections, right? And let's say you're executing lock A on this core, and there's unlock A, and another core actually starts executing lock A over here, and it needs to go to unlock A. If we're going to parallelize this, these parts will execute in parallel, and whatever is read here should not the read set, all the memory locations that are read over here should not overlap with the write set of this, and vice versa, right? The read set of this critical section should not overlap with the write set of this critical section, and also the write set of this should not overlap with the write set of this, right? Read sets can overlap with each other. The read set of this can overlap with the read set, but there should not be a conflicting write. There should not be a happen before relationship that is violated here, because the critical section semantics is either the entire thing is executed or none of it is executed. It cannot receive a value coming from this critical section over here. Okay? Basically, somehow you need to keep track of dependencies. And there are many ways of doing that. Actually, you could keep track of whether or not there's a conflict between these two critical sections by using the coherence protocol. Remember, thread level speculation used coherence protocol to detect the conflicts when some other thread actually requests this cache block as read exclusive. Then the cache block's read and write bits are set, and if any of them are set, this means that there's a data conflict and one of the threads is aborted, right? In this case, one of the threads will go back to the beginning of the critical section, right? Okay? How do you buffer the speculative state? This is very similar to what we've discussed, basically. If you're actually having writes over here, having stores over here, what do you do with those stores? You should really not expose them to any other part of the system, right? Because you do not know whether or not this critical section will execute or not. The execution should be atomic. You should only expose these stores at the very end of the critical section over here. And this requires buffering of the state, and we've discussed how to buffer the state, right? Address resolution buffer was one example. You could buffer in the cache. Of course, you need to change the coherence protocol such that this doesn't get exposed to other parts of the system. Okay? How do you check if atomicity is actually violated? How do you actually figure out the dependence violations, right? Using the coherence protocol was one example we've discussed earlier, what I discussed just now. Or there's an alternative strategy, right? Maybe you actually keep track of the addresses that you read and addresses that you've written to, and you accumulate that in some data structure until the end, until right before the unlock. And then at the very end, you compare those addresses to all of the other addresses that you've seen in the critical sections that are currently executing in the system. So this is a different approach. You don't detect the conflicts right away, but you actually detect them by comparing these sets, read sets and write sets. And you can actually implement these read sets and write sets using Bloom filters, right? You will be approximate, but approximate is okay over here, right? Why? Basically, whenever you can have a Bloom filter for the read set. Whenever you read an address, you set a bit corresponding to that address, and that bit vector can be small. Whenever you write to an address, you have another Bloom filter This is the read Bloom filter, and this is the write Bloom filter. Whenever the critical section writes to an address, it writes, sets the bit corresponding to that address. And at the end of the critical section, these Bloom filters for this critical section are compared to the Bloom filters of all of the other critical sections that are currently executing in the system. And if these Bloom filters actually overlap somehow in a bad way, in a data conflicting way, which means read sets overlap with write sets and write sets overlap with write sets, potentially, then a conflict is detected and you know which transactions actually, or which critical sections conflict, and the system can abort one of them. So that's one other way of detecting conflicts. And people have proposed many different ways, and I would encourage you to think about different trade-offs associated with it. Later, how do you support commit and rollback? Basically, at the end, you need to somehow either commit or abort. Or do you abort early whenever you detect a conflict? If you detect the conflict eagerly. So there are many concepts over here. You can detect the conflict eagerly or lazily. And we will get back to this. Eager detection means whenever some other thread reads a cache block that is written or read, whenever some other thread basically requests this cache block in a read exclusive manner, you know that there's a conflict, right? You can easily detect that conflict. That's the detection. Or you could detect the conflict at the very end, as I discussed to you. That's the lazy detection, right? This is the lazy detection approach. Detect the conflict at the very end of the transaction or the critical section. Eager approach, detect the conflict as it happens at that time. And then there is a question of when do you handle that? When do you handle the abort, for example? Whenever you detect it, or do you delay it at the very end? There's a trade-off here, right? If you abort a transaction, if you abort a critical section, right when you detect the conflict, that critical section may not finish, right? Because you may be using a policy that's not optimal. Because some other thread may always be conflicting with this critical section, right? You may run into starvation issues. So with eager handling of conflicts, you may run into starvation issues. But it's quick to react, right? When it figures out the conflict, there's no reason to continue this transaction or critical section, right? You can quickly react. And if the starvation is not an issue, this can be higher performance. Whereas lazy doesn't usually run into starvation issues because you can, at the end, handle in a calm head, right? See, oh, what have I done? Let me figure out which transaction or which critical section to abort, actually, so that I'm fair, right? So this is less starvation issues, but this could potentially be lower performance because the reaction time is slow, right? Basically, lazy conflict handling, lazy aborts can lead to slow reaction time. Right? But many of the issues over here can be classified as eager and lazy, and I'd encourage you to think about that also. Basically, how do you support commit and rollback? How do you actually, when do you actually abort, for example? How do you go back to the beginning of the transaction or beginning of the critical section? I keep using the words transaction and elided lock, speculative lock elision, in a sense interchangeably because they're very similar concepts. But somehow you need to be able to support going back to the beginning. And usually that's supported via a checkpoint, register checkpoint. Because you don't update memory, you don't need a memory checkpoint. You buffer the speculative updates, right? You usually support that using a register checkpoint. And if there's a conflict, one of the transactions or one of the critical sections goes back to the checkpoint. Right? So this is another important issue. Okay. So, basically, what we're really trying to do is to maintain atomicity, right? If atomicity is really maintained, then all locks can be removed. So what are the conditions for atomicity? Data that's read is not modified by another thread until critical section is complete. Right? Or data that's written is not accessed, either read or written to by another thread until critical section is complete. So that's what conflict detection is all about. Basically, if we know the beginning and end of a critical section, we can monitor the memory addresses read or written to by the critical section and check for conflicts with other parts of the code. If there's a conflict, we can detect it using the underlying coherence mechanism, right? And That's what the SLE paper that I've assigned you actually talks about. How to use the underlying coherence mechanism to detect the conflicts. This is very similar to what we've discussed with thread level speculation. It's a scalable approach to thread level speculation paper. So let's take a look at the implementation a little bit. I'm not going to go into a lot of detail on SLE implementation, but basically the processor checkpoints the register state before entering speculative lock elision mode, and decides to enter speculative lock elision mode by detecting the lock. In speculative lock elision mode, if there's a store in the critical section, basically, the processor buffers the updates in the write buffer, in the store buffer, and doesn't make it visible to all other processors, but requests exclusive access for that particular cache block that it's trying to store to. Right? That's the idea. So let me actually clean this up so that you can see a better picture of this. I'll get back to this eager versus lazy, so keep that in mind. A lot of the issues that we will discuss can be handled eagerly or lazily. Basically, the processor detects the lock, checkpoints the architectural state, and keeps executing, and there's a store, and this store goes into the write buffer, and also it sends a read exclusive requests in the coherence protocol. Right? When there's a store or load that happens, this also sets the access bit. In this case, the paper talks about access bits. Basically, you have one bit called the access bit, not the read-write bits. You could have read-write bits, but this access bit is set whenever you do a store to a cache line or a load. Right? And the system triggers misspeculation on some coherence actions. What are those actions? This is very similar to what we've discussed earlier. If there's an external invalidation to a block with access bit set, so if there's a coherence request that says invalidate this block, and the access bit is set, that means that there is misspeculation because somebody else is trying to access that block, or actually write to that block, or acquire that block that this particular processor executing this critical section actually has written to or read, right? Which means that there's a data conflict between two critical sections, or this critical section and other parts of the system, other parts of the code. Or if there's an exclusive access, not only invalidation, but also read exclusive. This is basically intention to actually write, to request a block with the access bit set, right? So that's the idea. And also, if there's not enough buffering space, this particular implementation triggers misspeculation. So what does that mean? Basically, you have lots of stores here, ... store, and eventually you run out of your write buffer entries, right? You cannot put this latest store into the write buffer entry because there are no write buffer entries left. Well, in this case, too bad, the system says. I'm going to trigger misspeculation, go back to the beginning of this particular critical section. Similarly, whenever misspeculation is triggered because of an invalidation or read exclusive written received to a cache block that has the access bit set, the processor goes back to the checkpoint it has taken at the beginning of the critical section, at the beginning of the SLE mode. Okay? And if end of the critical section is reached, which means that the processor detects unlock over here, if this end is reached, without misspeculation, all of the writes that are in the write buffer are committed. And this needs to happen instantaneously. Right? That's the idea. It needs to become visible to all processors as committed right away. All of their processors should be able to get those values without atomically. Basically, all of these stores need to happen atomically. Right? So that's the key idea. That's the implementation of speculative lock elision. It's very simple, conceptually easy, and let's actually compare and contrast this with accelerated critical sections. We've actually seen a different way of handling critical sections, which was accelerating them. Basically, whenever you get to a critical section, take the critical section and ship it to a large core such that you can get out of it fast. Right? SLE says, whenever you get to a critical section, basically elide the critical section. Keep executing and check for data conflicts. Right? There are advantages and disadvantages of both approaches conceptually as well as implementation-wise. In this slide, we talk about some conceptual differences. Accelerated critical sections has several advantages because it can speed up each individual critical section. Right? If you think about it, you actually speed it up by sending to a large core. At least that's the goal of accelerated critical sections. Whereas speculative lock elision is more for latency hiding. Basically, instead of serializing the critical sections, why don't we parallelize them such that we can hide the latency of these two critical sections? That's the idea. So ACS is an advantage. And ACS works even in the presence of data conflicts, right? If there are data conflicts, actually shipping them to a large core and serializing them there is a good idea, perhaps, because you don't compare it to SLE. Whereas SLE, speculative lock elision, if there are data conflicts between critical sections, it incurs re-execution overhead. One of the critical sections need to abort and re-execute, right? So that's one advantage of ACS over SLE. It doesn't incur re-execution overhead since it doesn't speculatively execute critical sections in parallel. Right? And the third advantage is accelerated critical sections actually can keep shared data and locks in a single cache. It can improve shared data and lock locality. Whereas this doesn't exist in SLE, because in accelerated critical sections, every critical section is executed in a single place, single core, with hopefully a large cache. Whereas with speculative lock elision, every critical section is still executed in one, in a different core, right? Wherever it happens to be executed, basically. Okay, but accelerated critical sections also has disadvantages over speculative lock elision. One is, whenever you ship the critical section to a large core or somewhere else, you need to transfer the private data and also the control to a large core. This reduces the private data locality, and which we've discussed when we talked about data marshalling in the asymmetry lecture. So I'll encourage you to go back and look at that, and this incurs overhead. This overhead is not present in SLE. Speculative lock elision, private data stays wherever the critical section is executed, right? The other advantage of accelerated critical sections, it's whenever there's no conflict between the critical sections, speculative lock elision just makes sense, right? It basically keeps going, and it can parallelize these critical sections that would otherwise be executed serially. Accelerated critical sections doesn't do much about that. Even though there's no data conflict, the critical sections are serialized. And finally, accelerated critical sections use a mechanism that uses a large core and dedicates that large core for critical sections, and that large core can actually reduce parallel throughput. But we've discussed that if you actually add SMT, simultaneous multi-threading, to that core, you can reduce that effect of the loss in parallel throughput. So these are some conceptual advantages and disadvantages of accelerated critical sections. And these, some of the conceptual advantages and disadvantages are actually talked about over here. Basically, this is a section 8.2 from Suleiman et al.'s Accelerated Critical Section Execution with Asymmetric Multicore Architectures paper, which you read, and I'd encourage you to look at it again. Basically, it compares ACS to transactional memory, speculative lock elision, and transactional lock removal, and speculative synchronization. And these are actually approaches to parallelizing critical sections, synchronization constructs. And the idea is, as long as the synchronization construct, the same instance of the synchronization construct, doesn't have a conflict with another instance, these can be executed in parallel. So these enable the hiding of the latency of the synchronization, right? ACS actually is partly orthogonal to these approaches, this paper states, because when the critical sections have conflicts with each other, these approaches do not work because they need to roll back speculative execution to the beginning of the critical section, right? For all of the instances of the critical section except for one, right? Whereas ACS, regardless of however many data conflicts you have, it still obeys the locking semantics, right, in execution. As a result, it serialized the locks, serialized the instance of the same lock. Basically, the big difference is these are latency hiding mechanisms. Accelerated critical sections is hopefully a latency reducing mechanism for critical sections. And also the locality improvement that you get with ACS is not there with SLE or transactional memory as we see it, because accelerated critical section, these approaches do not execute synchronization constructs in a single place. So I'd encourage you to think about some of these advantages and disadvantages. And I'll not cover this, but this paper shows that accelerated critical sections for the critical section intensive workloads with not a lot of, with some data conflicts, actually accelerated critical sections performs better. But of course, there are advantages and disadvantages to these two different approaches, and potentially you can combine both, right? One accelerates the locks, and the other elides the locks, or synchronization constructs, let's say. The key question is, how do you actually combine the both? I'm not going to give you the answers, but I'll pose the questions because these could be actually very good projects if you're interested in that as well. Can you do better than both? How do you actually decide whether to accelerate a lock or elide a lock? For example, I'll give you a hint. If you can actually predict when you get to lock whether you will have a data conflict. And if the outcome of that prediction is, yes, it's likely that if I execute this critical section, if I elide this critical section, I'll have a data conflict. And if it's on the critical path, then you ship it to the large core, right? Because it's important. If it's a critical section, it's a bottleneck critical section. Whereas when you get to the critical section, the prediction is that, oh, I haven't seen a lot of data conflicts for this critical section. Let me keep executing. Let me elide this. Then you pick speculative lock elision. So perhaps you can do better than both by combining both ideas. And sometimes you may want to elide the lock. Sometimes you may want to accelerate the lock. And sometimes you may want to do nothing about it, right? Because shipping it to a large core may incur more overhead than the benefit you get from the large core. Okay. So I've covered speculative lock elision, which is a very promising way of actually improving the performance of parallel programs by hiding the latency of critical sections. And we have already looked at accelerated critical sections, which was actually not a speculative mechanism. So the difference between speculative lock elision and another difference, more implementation difference, is speculative lock elision is speculative, whereas accelerated critical sections is really not speculative, because it really obeys the locking semantics. It doesn't really try to parallelize the locks, whereas speculative lock elision tries to parallelize the same lock. So let's go back to some of the four issues that we've seen in speculative parallelization before. Remember, there were four issues in speculative parallelization, and these are actually applicable to speculative lock elision as well. These were applicable to speculatively parallelizing a single-threaded program as well. So first issue, how to deal with unavailable values. Do you predict them or do you wait for them? Well, actually in speculative lock elision this doesn't happen, because the program is already parallelized, and because you're not cutting the program already, the values are available. You're not really making things, you're not really trying to partition the program at a point where some value is not available. The value is already available, you're trying to elide the lock. Right? So that's the idea. So this issue doesn't exist as much in speculative lock elision. Although you could view the potentially dynamic data conflicts between two critical sections as an unavailable value for another instance of that critical section. But we're not going to view it that way. We're going to view that as a conflict. The second issue is how to deal with speculative updates. Are you actually eager when you do speculative updates, or are you actually lazy? Eager means basically you update the original location and you log the old value. And then when you abort, then you need to undo from the log. That's a very aggressive way, right? Eager's advantage in this case is you update the original memory location such that that update becomes visible. You don't need to deal with re-updating the location at the very end. Now, lazy means you buffer your updates somewhere and do not expose them yet to the original location. Now you have multiple copies, right? If you do buffering, you have multiple copies. If you do logging, then you have the original copy is always at the same place, but you have a backup copy that you need to go back to in case there's a data conflict. With buffering, you're lazy. You basically postpone the updates until the end of the critical section. Postpone the stores until the end of the critical section. The advantage is you don't expose them quickly. The disadvantage is now you need to ensure that at the end they're all exposed at the same time. Right? That's the idea. So eager versus lazy applies over here too. And in the approach that we've discussed, speculative lock elision does it lazily. Right? How to detect conflicts? Again, we've discussed that. Do you detect them eagerly or lazily? Right? Do you detect them right away, or do you actually lazily keep track of reads and write sets, and at the end of the critical section, you compare the reads and write sets and to figure out whether or not there are conflicts. And finally, how and when to abort or roll back or commit. When do you decide that? How to abort? Do you abort eagerly or do you abort lazily? Eager abort means you abort right when you detect the conflict between the transactions or between the critical sections. Lazy abort means you wait until the end of the transaction. At the end, you figure out which transaction to abort. Right? Here, because you can always abort one or the other. Right? It's not clear which one to abort. And sometimes it may not be, it may be very unclear when you have many different transactions running at the same time, many different critical sections instances running at the same time. How to commit is easier actually, because you need to commit at the very end, right? And that's important. There's one other issue, basically whom to abort actually is important, because and when to restart is also important, because you want to ensure starvation freedom, and you want to ensure fair progress for different threads, for different transactions. You don't want to abort all the time the same poor transaction, right? If that's the case, you'll run into starvation issues. So doing this conflict handling in a way that's fair as well as high performance becomes an interesting research area in speculative lock elision, as well as transactional memory approaches that we will talk about later. Basically, the takeaway is eager versus lazy approaches are possible for each of these issues, and I encourage you to think about different approaches and their trade-offs. And there has been a lot of literature in this field, at least in transactional memory, maybe less so in speculative lock elision, but in transactional memory, that deals with these 4 different questions in speculative parallelization. So let's take a quick break, and then finally we will cover transactional memory, and after that we're going to finish our module on speculation in parallel machines. Okay, now that I've covered speculative lock elision, I'll briefly cover transactional memory, but transactional memory is actually speculative lock elision exposed to the programmer, and that's actually a good way of thinking about it. It does change the programming model significantly because it doesn't keep the lock-based programming model, but a lot of the ideas of transactional memory are actually very similar to speculative lock elision that we've discussed earlier. So I'm going to go through this relatively quickly and defer you to the papers that I'll discuss, as well as some of the other literature that we will put up online. But I'd be happy to take any questions related to this and give you potential pointers in terms of potential research topics. But the basic idea is, remember, we want to keep atomic execution of critical sections. And the basic idea here is programmer specifies what code should be executed atomically as transactions. And hardware and software guarantees atomicity for these transactions. Which means that the programmer doesn't need to deal with locks anymore, right? The programmer, all they need to do is delineate the transactions, or what code needs to be executed atomically. That's it. There's no need for the programmer to lock individual buckets of a hash table. Remember that hash table example that I gave you earlier? There's no need for the programmer to do fine-grained synchronization, fine-grained locking. The programmer can say atomic hash table update, right? Atomic hash table read. I guess so there's a bunch of code that does hash table reading somehow, and a bunch of code that does hash table updating over here. And this doesn't need to be atomic. Another way of thinking about it is begin transaction and end transaction at the very end. Right? You could use begin transaction and end transaction. Right? And somehow the hardware and software guarantees that this entire piece of code is executed all or none. And how does it do that? Well, similarly to what we've discussed earlier. This is motivated by the difficulty of lock-based programming. Lock-based programming is not easy, as we will discuss in the next slide. Programmers make mistakes because they need to protect everything with locks. And if they want to get high performance, and locks cause serialization, right? That is a form of blocking synchronization. When a thread acquires the lock, all of the threads that need to acquire that block, that lock need to block. Basically, locks lead to blocking synchronization. Threads block, waiting for the lock. And because of this, you want locks to be small as possible, the critical sections. But if you want to make the critical sections as small as possible, it becomes harder. Now you get into buggy programs. This is the fundamental trade-offs that we've discussed earlier. Much of parallel computer architecture is about enabling the programmer's job to be easier when writing high-performance parallel programs. So that high performance comes from reducing the size of the locks, and it's difficult to reduce the size of the locks because now you get into bugs. What if you incorrectly exclude something out of the critical section, whereas that is important for correctness to be inside the critical section. Whereas, well, one way of getting rid of that problem is having a single lock for the entire program, right? For main, beginning of main, you say lock. At the end of main, you say unlock. And all the threads do that. Now, this is terrible for performance, right? Because every thread is serialized with every other thread. You don't want that. That's really bad. Transactional memory kind of gives that illusion in terms of programming, but it's really easy to program the first one. You don't need to reason about any conflicts, any potential shared data updates at all. Transactional memory kind of gives that illusion to the programmer, right? Basically, you can have a large atomic block, and the underlying hardware of the software determines which atomic blocks can be executed concurrently without violating atomicity. That's the idea. Transactional memory is also motivated by the lack of concurrency in blocking synchronization. And we've kind of talked about this, right? Blocking synchronization leads to lack of concurrency because you need to have serialization. But there are many cases where serialization is dynamically unnecessary. If you had atomic constructs like this, begin transaction and end transaction, then the runtime system can decide which transactions can be executed in parallel in an underlying manner. There's no reason for the programmer to synchronize, serialize these different accesses that are that do not require necessary synchronization dynamically. So another form of term, basically, this blocking synchronization is locks, whereas non-blocking synchronization is transactional memory, or because when you get to a critical section, atomic block, you don't block, right? You don't actually wait for someone else to release the lock because there's no lock, okay? Also, transactional memory is called optimistic concurrency, whereas locks are called pessimistic concurrency. Why? Because locks are really serializing every access to that shared data structure they protect, right? This is kind of pessimistic, right? What if those accesses do not conflict with each other, right? As we've seen earlier. Whereas transactional memory is optimistic because there's no need to really serialize the atomic blocks. Execute the blocks, and if there's a data conflict, you detect that conflict. It's kind of optimistic in the sense that it works best if there are no data conflicts, and that's kind of the assumption, right? The data conflicts is rare, so we're going to elide the locks. We're going to execute these transactions in parallel. And only if they conflict with each other, we're going to detect that conflict and roll back one of them. Okay? So let's take a look at these locking issues in a little bit more detail. Locks are not great programming constructs, even though they work well. They have some issues. They have some problems that make it difficult or low performance to program with them. Basically, what's a lock? Lock is an object only one thread can hold at a time to enable synchronization. For example, you can have a lock for each shared data structure, or you can have a lock for a portion of a data structure, maybe individual nodes in a linked list. That'll be hard to program, right? Maybe individual buckets in a hash table. That'll be hard to manage. The usage is a thread waits for acquiring the lock, which means that it can block for a while, waiting for the lock, and then it acquires the lock. It basically writes to a memory location, for example, or it can be a counter-based lock. You can increment a counter. It accesses the critical section after that, and once the critical section code is done, it releases the lock. That's the model. This leads to several issues. One is correctness issues, and the other is performance issues. And we'll take a look at both. Correctness issues, if you want high performance, well, you may sometimes need to forget a lock, right? This leads to underlocking, right? Basically, this leads to data races, and sometimes you get incorrect behavior because you may have forgotten a lock. Why? Why do you usually forget a lock? Well, you may be careless, yes, but sometimes you actually forget to protect some part of the code that needs to be protected because you're really trying to optimize performance in this code. And to optimize the performance in this code, you want to minimize the serializing constructs, which means that you want to get rid of those critical sections that are large. That leads to underlocking, that leads to data races, and that leads to bugs that are necessarily, that may actually lead to incorrect execution. Right? So data race means basically you have accesses to shared data that is done concurrently by different threads. This is not necessarily a bad thing, right? This may not be a bad thing. for example, accesses to locks are actually data races, right? When somebody is writing, some other thread may be reading from it, and that data race is necessary for synchronization. But for regular shared data, it may not be a good thing, because when one thread is updating that shared data, you may not want another thread actually reading that shared data. That's the whole purpose of synchronization. For example, when one thread is inserting to a linked list, you may not want that other thread to read from that linked list, especially if that read and insert will not be consistent. Right? Will not achieve the semantics you would like to achieve with that read and write. The second correctness issue is acquires in different orders. I'm not going to go into this in detail, but if you're actually protecting multiple different structures, you may get into a situation you have different orders of acquires. One thread may acquire lock A and wait for lock B in that order, because the control flow happens to take that thread that way. So it's going to acquire lock A, acquired, and then it can wait for lock B. Another thread can acquire lock B, and it gets to wait for lock A, but this thread is holding lock A, and this thread, so it cannot make progress. Whereas this thread is waiting for lock B, and this thread has already acquired lock B, so this cannot make progress. Too bad. Now we have a deadlock, right? No thread is making progress. This happens because you have different locks for different structures, and if you had a single lock, it could reduce your concurrency, right? That's the problem. You may actually want to protect only this data structure sometimes, and then you want both of the locks to be acquired when you want to protect both of the data structures when you're doing something with both of them. So this leads to deadlock. Whereas if you have a transaction begin and transaction end, this doesn't happen because there is no acquire and release. There are no different locks. Basically, somebody guarantees that atomic execution is satisfied. Let's take a look at the performance issues. Well, as I told you, locks lead to conservative serialization. There is also overhead of acquiring the locks, right? If some other thread is actually holding the lock, that lock needs to be brought to the cache of this other thread that's executing in this other core. So it takes time to acquire the lock. So there's ping-ponging that happens because of the locks. It's difficult to find the right granularity of locking exactly because of what I discussed, right? If you actually make the locks coarse grain, it's easier to program, but lower performance because of the overheads. Whereas if you make the locks fine grain, it's harder to program, and the performance is higher potentially, but there may be correctness issues. And blocking synchronization is the cause of a lot of these issues. So let's compare and contrast locks and transactions. Remember, in locks, we had underlocking issues because the programmer needs to minimize the locks because they cause serialization. Transaction can help this because the interface is simpler, right? The programmer doesn't need to reason that much about what is really shared data and what's not shared data. They do need to reason about what needs to be executed atomically, but they can be a little bit relaxed about it because atomic means all or none. And if the programmer wants, the atomic can be a larger code section. Whereas with locks, you have blocking synchronization, so the programmer, it's difficult for the programmer to reason about that interface, right? And reason about what will happen when they reduce the size of the critical section, right? Locks have deadlock due to lock ordering, whereas transactions have no ordering of locks because there are no locks to begin with, right? As we discussed. Right. There can be no deadlocks in transactions unless the transactional memory manager somehow does a wrong thing. But that's not the responsibility of the programmer. Right. Locks lead to blocking synchronization, whereas transactions are non-blocking, as we discussed earlier. Right. Basically, whenever there's a conflict, one of the transactions actually abort, and the transactions go into the transaction is executed optimistically, as we've discussed. And finally, locks have conservative serialization. They have forced serialization all the time, whereas basically for different instances of the same critical section, they're conservatively serialized even though serialization may not be necessary dynamically. Whereas transactions serialize only on conflicts. Right? The conflict is detected dynamically and serialization is then forced if there's a conflict. Whereas if there's no conflict, two transactions can execute concurrently. And that's the idea of optimistic concurrency versus pessimistic concurrency that we've discussed. So transactional memory, if you think about it, it allows arbitrary multiple memory locations to be updated atomically in an all or none fashion. And there are several basic mechanisms which we've already covered actually, so I'm going to briefly go through these. One is you need to provide isolation and conflict management. You need to isolate these two transactions from each other. Right? Whenever this transaction is executing over here, this transaction should not see its state because this is not updating that state. And the other parts of the system should not see the updates, which means that you need to do buffering. Right? You need to track reads and writes per transaction. And you also need to detect conflicts between transactions. And we've discussed this earlier. Version management, you need to record new and old values because you don't want them to be exposed, new values to be exposed to the other parts of the system. And we've talked about this in detail when we talked about SLE, Speculative Lock Elision, earlier. And there are eager versus lazy ways of doing that, right? You could record the new values in a log or in a buffer, right? Okay, and atomicity is another mechanism that needs to be provided. Basically, the transactional memory provides a mechanism for committing new values or aborting back to old values. You have all or none semantics in a transaction, and that's what's really important, just like speculative lock elision as we discussed earlier. So issues are actually the same as other speculative parallelization schemes. Remember the four fundamental things? Actually, I have three over here because one of them doesn't exist, and you can think about what that is while you're listening to this video. Logging and buffering, conflict detection, abort, rollback, or commit. And remember, these were the four things. How to deal with unavailable values. Do you predict them or do you wait them? This doesn't exist over here, really, because the values hopefully are available. But how to deal with speculative updates? Do you do logging or buffering? How do you detect conflicts? Do you do it lazily or eagerly? Do you use the coherence protocol? Or do you actually keep track of read sets and write sets and potentially Bloom filters? How do you, and when do you do the abort and rollback and commit? And also, who do you abort on a conflict is important. Do you do it eagerly and lazily? Do you have a manager that actually manages which transactions, which threads should commit its transactions? What kind of quality of service and what kind of fairness guarantees do you give to the transaction manager? Basically, these are all can be considered transaction scheduling, if you will. Which transaction do you actually abort? Which transaction do you commit? Which transaction do you restart? And again, we've covered this a lot in the Speculative Lock Elision lecture. You can go back to it, and a lot of the issues are similar with transactional memory and speculative lock elision. But there's an abundant set of papers that look at conflict management and transaction scheduling in transactional memory, and I'd encourage you to look at those if you're interested in this. There are many variations of transactional memory as well. This can be implemented purely in software, which means that the runtime system somehow ensures that you actually satisfy these atomicity semantics in the transaction, right? So the upside of this is there are no virtualization issues, right? All of the addresses are virtual. If you actually interrupt the process, well, you can actually keep track of everything in software, right? Basically, what are the issues with actually virtualization? Let's say you get an interrupt in the beginning, in the middle of an atomic code block. It's okay if you have everything handled in software, right? Because software actually, the state of this program is saved somewhere. So all of the information that you keep track of about the read set and the write set are saved in software. So for example, when you do read, write, if you have software transactional memory, these need to be kept track of in some data structures that keep the read set and the write set, right? And these data structures are part of the program, and when the program is interrupted, those get saved somewhere. So automatically virtualization is handled. The downside of software transactional memory is its high performance overhead. All of these operations that we've discussed earlier need to be done in software. Conflict management, read write set tracking, abort management, all of them is purely software. And that adds a lot of overhead into the system. On the other hand, hardware, the upside is low performance overhead. Everything is done in hardware. Coherence protocol specifies, for example, is modified such that you abort transactions easily. The downside is now you need support for virtualization in hardware. Right? For example, what if your buffering for writes are not enough in hardware? What do? You don't have enough buffers for writes? Well, you may need to virtualize. If you want to support a large transaction that writes 1 million memory locations, where do you write those? Well, maybe you virtualize those buffers, right? Now this becomes more complex. This also virtualization is also needed when you get a context switch in the middle of a transaction. What if you have a long-running transaction, right? And you want to take the context switch, and the transaction is running in hardware. Now you have these hardware structures that are buffering the data. For example, the read-write bits in the cache. What do you do with them? Too bad, you cannot blow them away because they belong to this transaction and they affect correctness, right? So when you get to a context switch, do you actually abort the transaction then? Well, that may not be a good idea because the transaction may be actually a long transaction. So what if you will eventually need to complete it, but what if it gets a context switch again? So you run into these issues of virtualization when you have pure hardware transactional memory. And this actually should be HTM over here. So I'm going to modify the slide right here, if you will, and actually even save it. Okay. So, and what happens when you do I/O within transactions, right? When you do I/O, you usually context switch. How do you handle that? How do you serialize these transactions when they're hardware, when the transactional memory is purely in hardware? So because of these issues, again, you have upsides and downsides as you see between software and hardware. People have looked at hybrid hardware-software mechanisms, and as you can imagine, it's a heterogeneous approach. Basically, the basic idea is when buffering is enough and there's no I/O or context switch, use hardware transactional memory such that you get low performance overhead in executing transactions, and switch to software transactional memory to handle long transactions and buffer overflows and I/O and context switches, basically. That's the idea. And I'd encourage you to read papers related to it. There's been significant literature on this. Let's go back to the beginnings a little bit and talk about some of the initial TM ideas and current implementations very briefly, and then we'll conclude transactional memory in particular and speculation in parallel machines in general. Transactional memory is actually inspired by load-linked store conditional operations. And Jensen paper from Lawrence Livermore National Lab Technical Report in 1987 is the first one that introduced this. But the basic idea is to have an instruction that does an atomic update of a single cache line without any lock. We don't want any locks. We want to update the single cache line. How do we do it with some new instructions? And that's the idea of load-linked and store conditional operations. This is used to implement non-blocking synchronization in existing ISAs. Alpha and MIPS are the first, some of the first ones to implement it, but the ARM and PowerPC have this. x86 has a form of it. The basic idea is you have two instructions, load-linked. Load-linked instruction, LL, returns the current value of a location. Let's say load-linked memory location A into R1. Okay? And then a subsequent store conditional to the same memory location will store a new value only if no updates have occurred to the location. Okay? And then you do store conditionals, new value, right? And then you give it R1 and then memory location A, right? Okay? And this basically ensures that if someone has updated the memory location A between this load and store, you figure that out, right? Because this store doesn't succeed if someone has updated. Now you can check whether the store succeeds. I've butchered the semantics over here, but you can check if the store succeeds, and if the store doesn't succeed, you can keep doing this. If no success, which means that somebody has perturbed with the memory location, there was an update to the memory location, and the value of the memory location changed, which means that somebody else must have changed it, then you keep going back, and this is the programmer needs to do this, of course, loop, and keep loading. Right? Whereas store conditional, if it succeeds, then you can keep going, keep executing. That's the basic idea. You enable the lock-free atomic update of a single cache line using these two instructions, and these instructions are supported. Then the key question is, how do you actually do lock-free atomic updates of multiple cache lines? And that's where transactional memory comes in. Hurley and Moss were in their seminal ISCA paper, which is assigned to you as required reading, introduced this idea of transactional memory. And you can view transactional memory is a way of providing atomic updates for multiple cache blocks or multiple words at the same time. In their implementation originally, instructions explicitly identified transactional loads and stores, and there was a dedicated transaction cache for buffering. Basically, buffering was not done in the cache, but there was a dedicated transactional cache. And unfortunately, size of the transactions were limited to this transaction cache. So if you had too many stores within a transaction that overflew this cache, too bad. You would abort that transaction and execute it in a non-transactional way. Or execute in a more protected way, right? In a lock way. Okay? So this is an example from the Hurley and Moss paper. I'm not going to go into this in detail, but basically what they say is our transactions are intended to replace short critical sections. For example, a lock-free data structure would typically be implemented in the following stylized way. Instead of acquiring the lock, executing the critical section, and releasing the lock, a process would use LT or load transactional to read from a set of locations, use validate to check that the values read are consistent. So there's no lock. You see, you start doing load transactional. And then you do validate to check that the values read are consistent. Validate means if no one has updated them, that's okay. They're consistent because they check the transaction cache. Use store to modify a set of locations, and use commit to make the changes permanent. If either the validate or the commit fails, the process returns to step 1. There you go. That's the atomic part of it. Okay? So you can read the paper in more detail. This is the beginning of transactional memory. Currently, there are many implementations of transactional memory. Some of them are in machines that have never seen the day of light. Some of them are in machines that you can actually buy and use today. Sun Rock was one of the earliest implementers of transactional memory. Remember, this was a machine that implemented run-ahead execution as well. And actually, the speculative lock elision and run-ahead execution had similarities that bear with each other. That's one of the reasons why Sun Rock amortized the cost of either one of them by implementing them together. They implemented run-ahead execution and speculative lock elision, or transactional memory. Why? Because transactional memory checkpoints the architectural states and keeps running ahead speculatively as well. Whereas run-ahead execution has a very similar approach. It basically checkpoints the architectural state and keeps running speculatively the program, right? So I recommend this paper that talks about early experience with a commercial hardware transactional memory implementation, which is Sun Rock's implementation. IBM Blue Gene, which is a supercomputer, also implements transactional memory, and this is a recent packed parallel architectures and compilation techniques paper that talks about its evaluation of hardware support for transactional memory in IBM Blue Gene. IBM System Z, another processor that's used in mainframes of IBM, implements transactional memory to ease programmers' job. And these are actually very parallel machines. That's one of the reasons they implement transactional memory. The idea is to ease programmers' job and also improve programmer productivity in programming these machines. So they have two types of transactions: best effort transactions. In this case, the programmer is responsible for the aborts, and guaranteed transactions that are guaranteed to execute. So guaranteed transactions are guaranteed to execute. They're subject to many limitations. For example, this transaction side length should not be more than this. Now, why are there these requirements? There are these requirements because the hardware structures, this implements hardware transactional memory. The hardware structures that are there to support transactions are of limited size. And if the transaction, for example, has a write set that's greater than the buffering that's implemented in this processor, too bad. The transaction will execute incorrectly, right? The programmer needs to guarantee that the transaction satisfies some of these requirements. And if that's the case, the hardware guarantees that the transaction will always execute correctly and atomically. On the other hand, if the programmer cannot guarantee that, they should use best effort transactions. The programmer is actually responsible for aborting transactions and doing their own conflict management. Now, as you see, this makes it a little bit harder to program with transactions. It's not that easy anymore, right? It was the easy abstraction, atomic, and executes beautifully atomically. Now, if you tell the programmer, you need to actually figure out how many cache blocks you're touching in your critical section. And based on that, I will guarantee you correct execution or not. Well, that makes it a little bit harder to program still. It's a different kind of reasoning that's required from the programmer at this point. Now, this may still be useful for many programmers that try to optimize their code because it can ease their job in doing performance optimization. But for the average programmer who has no idea, potentially, about how many cache lines, how many cache blocks are touched by a piece of code, it will be a nightmare, potentially. So it's important to actually virtualize the transaction. That's where the virtualization of the transactions becomes very important because if the transactions are actually virtualized, the programmer doesn't need to worry about how big their transactions should be. If the transactions are actually smaller, you get better performance because you don't run into virtualization. For example, you don't run into issues where you need to context switch out and need to save the transaction state. Right? So it's still good, even when you have transactional memory, to reduce the size of your critical sections. It's a fundamental issue. Size of the critical sections, the smaller, the better, because handling large transactions are actually costly in terms of both performance as well as implementation complexity. Intel Haswell has an implementation of hardware transactional memory. Again, it has similar limitations for it to get good performance on code. Intel Haswell also has speculative lock elision as well. And AMD also has a paper on their extension for lock-free data structures and transactional memory. So this is my last slide on transactional memory. There are many research issues on transactional memory. This was a very hot topic a few years ago with lots of papers being published in the architecture community. Now it's calmed down a little bit. It's being implemented in products, and it's not. It's clear that it's not a panacea to all parallel programming problems, although it could be a useful addition to the programmer's toolkit in designing better parallel programs. One issue is scalability. How do you actually scale conflict management and version management to a very large number of nodes? And I'll let you think about some of these questions. I'm not going to give you answers, but these are actually interesting research issues. The second is complexity. And complexity is mainly related to how to actually virtualize transactions without much complexity. How do you actually run long transactions and ensure that they execute correctly? In the presence of context switches and paging, how do you actually save transactional state? Especially if you have hardware transactional memory, how do you keep track of reads and write sets when you actually need to move the transactions to software if you have hybrid transactional memory? Handling I/O within transactions is interesting, and hardware complexity in dealing with all of this is interesting. Software transactional memory, pure software transactional memory, is unlikely to actually be very high performance enough to benefit a lot of programmers because there's a lot of overhead in managing transactions, read-write sets, aborts, commits, checkpoints purely in software. That leads to significant overhead, and people have tried to amortize and reduce that overhead with lots of optimizations at the software level and compiler level, but that overhead still seems to be very high. So hardware support for transactional memory is still needed, and once you start having hardware support for transactional memory, then the key question is how do you actually virtualize it? How do you keep that hardware complexity at check? Another issue is semantic actions. Basically, when you have atomic blocks that are nested with each other, what are the semantics related to that? I'm not going to talk about that, but this is more of a language and programming research topic. And finally, the key question, a big key question, is that transactional memory actually increase programmer productivity. Basically, the basic goal was to reduce the burden of the programmer in writing both correct programs and high-performance programs. And does this actually happen? And this is a difficult question to answer because there aren't huge chunks of programs that are actually converted to transactional memory. But a related key question is, does the programmer still need to optimize the transactions, optimize their sizes, and try to minimize the rate of conflict? And the answer is likely yes. But to what extent do they need to optimize as much as locks? It's less likely because locks have no latency tolerance. It's blocking synchronization. But this question is an open question, even though it's not a computer architecture class question where it's very hard to do a research project related to this. But I'd be very interested in listening to your opinions about what kind of potential projects you may want to do on transactional memory and speculative lock elision. So that brings us to the end of our lectures on speculation in parallel machines. We've covered a lot in speculation. We've talked about thread level speculation, and we've covered different approaches to parallelizing a single instruction stream, like dual core execution, for example. Slipstream processing was another example. And then we moved into using speculation to improve the performance of parallel program. We talked about speculative lock elision. We talked about transactional memory. And remember the four concepts of speculative parallelization that still exist. For example, multiscalar is an example that shows those four concepts. And I'd encourage you to think about potentially different ways of actually using speculation to improve performance, as well as efficiency, as well as productivity in parallel machines. This is another fascinating area in computer architecture.